Okay, so we've all seen those incredible videos, right? Humanoid robots doing backflips, folding laundry. It looks like the future is here. So why, after all this mind-blowing progress, aren't they in our homes doing our dishes? Let's get into it. I mean, you've got the Unitree G1, Tesla's Optimus, the Figure AI models. They're getting more and more capable, seemingly every single month. But the reality is, they're still stuck in the lab for the most part. So what's the holdup? What's the real reason you can't just buy one to clean your kitchen? A lot of people have this thought, and it makes total sense on the surface. We have these ridiculously powerful computers in our laptops and our gaming PCs, so why not just cram one of those super powerful chips inside a robot and, let it figure things out? Well, it turns out the problem is a whole lot trickier than just raw processing power. And that leads us right into our first big idea, what we can call the power myth. This is the assumption that just more brain power, more teraflops, is the only thing standing between us and a robot butler. Let's break down why that's not really the whole story. See, the real answer lies in three key areas that are way more challenging than just adding more processing cores. It's about a robot's physical reflexes, its ability to handle our messy, unpredictable world, and a brand new type of artificial intelligence that's only just now starting to hit its stride. So let's start with those reflexes. I'm not talking about thinking or making decisions. I'm talking about the simple, fundamental act of not falling over. This is a massive engineering challenge that folks in the field call the real-time control problem. To get this, you have to understand something called a feedback control system. It's kind of wild, but a humanoid robot isn't just walking. It's actually in a constant state of falling, and it's using this lightning-fast feedback loop to catch itself over and over and over again, just to stay upright. And the speed here is what's truly mind-boggling. This entire loop, sensors reading the robot's tilt, a controller calculating the tiny error, and then actuators firing the motors to correct it, all of that has to happen about 1,000 times every second. That's a 1 kilohertz cycle. It is an incredibly fast and precise dance of physics and code. And this is why you can't just stick your gaming PC's hardware into a robot. Your computer's operating system might pause for just a few milliseconds to handle some background task, and you would never, ever notice. But for a robot, a single millisecond pause breaks that critical balance loop. That one tiny pause is the difference between standing tall and a catastrophic fall. Oh, and not to mention, a 400-watt GPU would suck its battery dry in minutes. So the solution is super specialized hardware. A chip like NVIDIA's upcoming Jetson AGX Thor is designed for exactly this. I mean, it packs an absurd amount of AI power. We're talking 2,000 T-flops. But it's built from the ground up for real-time, uninterrupted operation, and it sips power at around 130 watts. This is the kind of gear that actually makes stable, untethered robots possible. Okay, so we have the specialized hardware for stable movement. That's one huge piece of the puzzle solved. But what about the software? A robot needs a completely new kind of brain to actually understand our world and, what we want it to do. And this is where a new type of AI comes into play, Vision Language Action Models, or VLAs for short. Now, unlike something like ChatGPT, which just crunches text, a VLA takes in a live video feed of the world and then outputs direct physical actions for the robot's body. It's the missing link that connects seeing with doing. And the progress here has been absolutely explosive. We are right in the middle of what you could call a Cambrian explosion for these models. You're seeing the big players like Google release their versions, but then, right behind them, comes this huge wave of open-source models that are making the tech available to everyone. This field is moving at an unbelievable speed. So we have the reflexes and we've got the new brain, but now we hit what might be the biggest hurdle of them all, teaching that brain how to deal with reality. This is what engineers call the simulation trap. So to train these robots, you can't just let them wander around your house for a few years. They'd break constantly. Instead, engineers train them in these super detailed virtual simulators. But the problem is what's called the sim-to-real gap. It's this enormous difference between how a robot performs in a perfect simulation versus how it does in our chaotic, messy, unpredictable world. In the simulation, everything is perfect. The floors are mathematically flat. The friction on every single surface is a known, constant value. And every virtual robot is a perfect, identical copy of the others. It's like a clean, sterile, totally predictable video game world. But your kitchen? Your kitchen is not a simulation. It has invisible grease spots that completely change the friction. It has tiles that are uneven by just a millimeter. There's dust and dog hair everywhere. Even tiny differences in manufacturing, like one screw on a robot being tightened just 0.01% more than on another one, can completely throw off an AI model that was trained in a world of perfect clones. These tiny imperfections are catastrophic. And this huge sim-to-real gap leads us to the final and, honestly, the most important problem. In the real world, when things go wrong, and they will, there's no undo button. I love this quote because it just nails the heart of the matter. When a piece of software has a bug on your computer, you can close it, restart it, hit undo. But when a physical robot has a software bug, there is no Control-Z. The consequences are real, and they happen in the physical world. And we're not talking about lightweight toys here. A typical humanoid robot weighs around 60 kilograms. That's about 132 pounds. That is a significant physical presence in your home, with more than enough force to cause serious damage to your property, your pets, or even a person. This really puts the stakes into perspective. When a chatbot hallucinates, you get a weird sentence. When an image generator messes up, you get a picture of a person with 6 fingers. But when a 130-pound robot has a logical error, that could mean a thrown object or a dangerous physical collision. The cost of a mistake is just infinitely high. So let's bring it all together. The reason you don't have a robot doing your dishes yet isn't because we have a simple lack of computing power. It's a much deeper, more complex set of challenges. It's a problem of real-time physical control. It's a problem of generalization from a perfect virtual world to our messy reality. And most importantly, it's a problem of guaranteeing absolute safety. We are finally, for the first time, giving these machines the brains they actually need to perceive the world around them. So the big question now isn't about making them smarter. It's about making them capable enough and safe enough to handle the beautiful, unpredictable mess of our daily lives. How long do you think that's going to take?